Distinguished Walter Dempsey. Walter got his PhD at the University of Chicago under Peter McCullough. So if you know, so that makes Walter, I guess, a real mathematical statistician, or else a disappointment to Peter, one or the other, or maybe both. And then he went to Michigan as a postdoc, and now he's at Harvard as a postdoc, and he's come to talk about at least exchangeability and in some context.
Thanks, Kerry.
And he probably has a bunch of awards and things like that.
Hi, everyone. Kerry said my name is Walter. So I do a bunch of different things. With Peter, I worked on some survival work and exchangeable survival processes. I work with Susan Murphy now, so I do some things with her related to, actually Peter and I did some joint modeling of survival and longitudinal data. And then with Harry, I switched from doing exchangeability on survival processes to exchangeability with respect to networks. So this is joint work with Harry Crane. And then recently I've been thinking of extending this work to more complex interaction processes. And so that's joint work with Brandon Ocelio at Michigan. And so this talk is called Statistical Network Modeling via Exchangeable Interaction Processes. I'll explain what I mean by exchangeable interaction processes, and then sort of go through a couple of different models that we're considering and some statistical properties of them. So the way I've outlined this talk is to first go over something which I usually skip, but I realized that this is sort of the way that Peter's made me think for a while, so I should talk about it a little bit, which is starting with invariance principles and how to incorporate empirical properties into my statistical models. I'll then go through how to define an exchangeable interaction network, and then I'll end with talking about hierarchical exchangeable interaction networks and apply it to an email data set that Kerry is familiar with. So, okay, so I thought I'd start with the way that I've been constructing statistical models for survival and interaction processes. So I usually start with statistical invariance considerations. Typically these are a Kolmogorov of consistency. This comes from this idea that Peter had of sample size being arbitrary, and so you want the model to be consistent when you sort of restrict down from, say, n+1 individuals to n individuals. Your statistical model should be consistent. Exchangeability is the notion in that the labeling of the statistical units is arbitrary, and we only label in order to distinguish among them. So I'm going to start one slide later with an example in survival analysis where the statistical units are quite obvious. They're the individuals that you're studying. And then I'll move on to the interaction processes where this notion of what is the statistical unit is a little bit more difficult, and sort of it actually leads us to the interaction processes we consider. Okay, so then after that we have empirical property considerations. So this is the idea that when you have a statistical invariance consideration, you usually prove a representation theorem, and it usually has some measures embedded in there. And then the question is, well, how should I define these measures? What measures should I use? And it really depends on the context, but you can put some natural restrictions on the measures depending on what you're doing. So in the context of survival processes, Peter and I talked about weak continuity, which is this idea that if I perturb the survival time slightly, my conditional distributions shouldn't change that much. And so that actually restricts the measures you choose quite substantially. In state-space processes, there's this notion of composability. In this networks context, what I'll be talking about, there's individuals like Barabazi who think of networks as sparse and having power law behavior. And so these are sort of natural considerations of limiting behaviors you'd like your models to have. And the last part, which Peter does not consider as much, but I think is very important, especially with the size of these network data sets that we're considering, are computational considerations. So there might be multiple models you may consider, but that all achieve these empirical properties and they satisfy your statistical invariance considerations, but some of them might be more amenable to computation, and so you're going to consider those ones as well. Okay, so what I'd start with, also, is there a clock in the room so I can stare at it, or should I just pull out my phone every so often? Oh, okay, perfect. Is that the right time? Yeah. So the first example I wanted to give, and it's just to give the ideas behind it in sort of a simpler case than the interaction process, is this notion of a multi-state survival process. So in the simplest case, you have survival times, which are times to which individuals pass away since recruitment, and we'll call them T1 through Tn. In a multi-state survival process, you can think of these individuals as being in a given state at a given time. So YUT is the state of patient U at time t. So the simplest case is failure, is the survival case, where this is a binary indicator of if they've passed away yet. You can think about more complicated settings in which you have individuals in different states. But overall, the main things I wanted to point out on this slide is that the labeling of the units is arbitrary. How I talk about unit U doesn't really matter, in the sense that if I call the person 1, person 2, person 3 versus 3, 2, 1 or 2, 3, 1, that actually doesn't matter. It's an arbitrary choice. And so this naturally leads to a notion of exchangeability, but, and this is why I went to the multi-state survival process, the labeling of time is obviously not arbitrary. So T, which indexes the time since recruitment, is not an arbitrary choice. Time 1 is different than time 0.5. So of course this just means that labeling is not always arbitrary, but the one that we care about, the labeling of the units, is arbitrary. And so the notion of exchangeability has to do with the fact that this labeling is an arbitrary choice. The second thing is that sample size here is arbitrary. So this n that we consider here, this n may be a function of things like just how many individuals you could recruit into your study. It may be a function of the power calculations you've done before. But the way that at least I think about the statistical model is usually it should be irrespective of your choice of sample size. And so you want to be able to say that if I restrict my model from m individuals down to n individuals, the model should be the same, or should be the same, or it should be a version of if I just looked at n individuals. So this is a restriction of the operator. And the last thing I'll mention here, this is the weak continuity condition I mentioned earlier for survival setting, is the idea that if I have epsilon perturbations, you're going to have the conditional distributions are going to be roughly equal. So if I have this epsilon small and the limit, you're going to retrieve the conditional distribution here. And the reason this is important is just this is one example of an empirical property you might want to have, or a consideration you might want to take into account. And this is going to put additional restrictions on the measures you choose. So the nice thing about survival analysis is that typically the units that you're studying are pretty obvious. So here, the units U are the patients that I've recruited. And so life is easy.
Carey.
Carey.
Empirical property, like, so that statistics will be robust? Is that what that's for?
Yes. So it's basically that if I treat all these individuals as potentially passing away at times t versus treating them as passing away at perturbed versions, that the analysis, the actual calculations won't change too much. Yes. And the thing that Harry and I talked about a lot is how to take this idea of what is a statistical unit and really think about it in the context of statistical networks. So I just picked some statistical networks to put up because they're pretty, but this is a slide just to transition into thinking about networks and interaction processes. So some examples of statistical networks are the following. So I'll be talking mostly about the top 3, mostly actor and enron, but in each case you have a data set with a given set of vertices. So in this case it's the actors, the edges are movies. In reality, so sometimes we'll call them edges. I might call them interactions depending, but edges and interactions, might use them interchangeably. In the Enron case, you have employees, and emails define edges between employees. If an employee A sends an email to employee B, that's an edge between A and B. In the Karate Club, I assume many people might be familiar with this, but these are social interactions between individuals in a karate club. And so you have club members and the social interactions of the edges, and so on and so forth. And the key point I want to make on this slide is in many settings, people will regard the vertices as the statistical units that they're going to consider. And so this is something that's very common, and it's adopted by a lot of the existing literature. In some cases it's totally fine, in other cases it may not be. And so what I'm going to propose is something slightly different, which is replacing the statistical units being the vertices with them being the edges, and I'll sort of motivate it as we go through.
So does it matter if the edges are directed or undirected?
It does matter, and I will try and make small comments depending on the situation. Overall, the way in which we model it should not. Let me think through before I say something. It'll affect things potentially when you get to the modeling phase, but in terms of discussion of units and exchangeability, it's not.
About if they're hyperim.
Yeah. So in the hyperedge case, what we'll show is you can prove a general representation theorem for interactions. When we get to the modeling, you actually will make assumptions about how the hyperedges form, and that will implicitly make assumptions about what it means to be a hyperedge, and I'll sort of go through that. Yeah. So the one I'm going to pick out in the next slide is the Karate Club data set, because it's old and pretty and small, and so it's easy to visualize. So this is the Karate Club data set. I think I just ran some type of block model on it before, but here you just have the vertices. You have each, so something that you might not know is actually there's multiple interactions between each guy, so I'll take this one, it's easiest to see. This vertex is some person, and they interacted 3 times with this vertex, so the multiplicity is shown in the number of edges you see. So a conventional thing to do that people do often is they construct a network, or construct a graph by first taking the vertices, and if there is an edge between any of these, they add it. So here you see I replaced these 3 by a 1, and then, and this took me a little while to do, so please appreciate the effort of the graph. So this is they then construct the graph by thresholding. So if you have an edge, that's because you've had at least one interaction, and then they analyze the resulting graph. So this is fine in some sense, and I'll go through potentially what can happen when you do thresholding of this type, but I'm not going to start there. So what they're really doing is they're taking the network, the observed network, in this case is the Karate Club, and they're replacing it with a graph. So they represent the network data as a graph with vertices V and an edge set E. The vertices correspond to the elements of the population, and the edges, there's a connection between two vertices depending on the setting, but in the case I was talking about before, the edge exists if there's at least one interaction between individuals I and J. And in this case, I'm going to assume no covariates, so it's a homogeneous population where xi is equal to xj for all ij and u. Now, this is not always the case. I'm going to mostly ignore covariates in this talk. You can ask the question at the end. I'll have some generic statement, but incorporating covariates in these settings is important, but it's very difficult. Okay, so there's a phrase by Cox and Hinckley that's relatively an old saying, but there should be model consistency with known limiting behavior. And so the key here is it's known limiting behavior. So what do we know about limiting behavior of statistical networks? This does not always need to be true, but in general, what Barabasi showed in one of his, I think it was a Nature paper, was that networks typically have power law degree distributions and have some level of sparsity. And so the degree of a vertex is just the number of edges it's contained in, so an indicator of I, J's, and E, and you go over, there should be a V over here. So it's the number of edges that V is involved with, and the degree distribution is pk, so pk is the number of vertices of degree k. And so if you go back and look at a lot of papers that talk about power law, you'll see plots like this, in which you have a log degree, log proportion plot, and you sort of see a line going through it. And the idea here is that the degree distribution pk is following a slowly time-varying function lk times k to the minus gamma. So gamma is your power law, and so gamma is greater than 1. And sparsity is usually saying something along the lines of the expected degree is growing sub-quadratically in the number of vertices. And so Barabasi and Albert come out and say, look, we think a lot of networks have the sparse and power law degree distributions, and so these are empirical properties you typically want to have your models have if you're going to be considering statistical models and data generating processes. So what's the problem? Well, I'm not going to start with a problem. I'm going to start with what would be natural statistical invariance properties that you may think hold based off of what you've chosen to be the statistical units. And then I'm going to show that, though, at least in the first case, before I get to my stuff, that actually doesn't achieve the empirical properties we set out to obtain. And then we'll move to my stuff, and I'll be able to say, positive things about what I work on. So let's look at the Facebook data set. So here we have all the individuals in Facebook that they've made into this nice, pretty picture. Let's suppose I sampled individuals from Facebook. So this population is quite large. There's a population of people using Facebook. It might be shrinking now because of all the Facebook stuff, but there's a large population. I've subsampled it. And I get to observe a network by constructing a network where the edges are friendships. So an edge exists between person I and person J if you are friends. So this is a very natural thing to do. And in this case, the statistical units that you're sort of thinking of are the vertices. You're sampling vertices. And so it's a very vertex-centric mindset, which is fine. So you sample n vertices. For every n, you have a statistical model on graphs with vertex set v, which is just 1 through n. And so you have n choose 2 possible edges you can put in. And so Pn is a statistical model of family of distributions on graphs of size n. And the thing that we've said already is that we're going to be sampling by sampling vertices. And so here the notion of consistency that I mentioned at the very beginning of the talk, what you can think of is if I sample m individuals, and then I restrict down to the first n of those, the model should be the same as if I looked at those n. So this is consistency under selection, is what we call it. And this makes sense when you're thinking of vertices as your statistical units. So this is selection sampling, statistical invariance property, and we should also assume that the labels I've given my vertices, 1 through n, should be exchangeable. Why I call them 1 through n is just because I need to label them to discuss how the graph is connected, but the labeling of them as 1 through n should not matter.
So,
yeah.
Still with the question.
Oh, no.
So you see the consistent, could you go back to
Oh,
the
sure,
first
sorry.
slide? So it's yn conditional m is...
Bad notation. So basically it's, if I take the yn, which is, this is good, right? Yeah. So yn is the graph that I get by sampling the first n individuals, and then I restrict it to just the first m. That is coming from the model piece of n.
Restricted to the first m is like the induced subgraph.
Yes, I induce that subgraph. And so here the notion is that if I did that, it should be the same as having sampled m individuals originally. So this is just to say one main point, which is why I made a big slide with lots of little text. So the key here is that when you assume consistency and exchangeability on the vertices, what you're really assuming is that the observed vertices comprise a representative sample of the vertices that are overall in the population. I've done simple random sampling of the vertices, and so the model that I'm looking at and the vertices I get to observe are representative of the ones I didn't get to observe. That's an implicit assumption with a lot of these exchangeable modelings. So typically if you're assuming exchangeability on the particular units that you've done, you're assuming a representative sample of those units. And so what has been proven a long time ago is that under vertex exchangeability with consistency under selection, you actually have these things called graphon models. And so a random vertex labeled network Y, so this is vertex labeled in the sense that you've labeled the vertices, is exchangeable if y sigma is equal in distribution to y, and what sigma is acting on is the labeling of the vertices themselves. So here you can see that these two networks are the same object, but here the vertices are labeled in one way and the vertices are labeled in another way over here. So we call a random vertex labeled network exchangeable if that relabeling does not impact the distribution. And so these graphon models work in the way where you have this phi function, which is a map from 0, 1, 0, 1 to 0, 1. And you can think of it as the probability of yij equal 1 given ui is just phi of ui uj. I don't want to get into the details here. What I want to point out, and this is the main point of putting it, is that under a vertex exchangeable network model, because you've assumed it's actually coming from a graphon, you're going to have that the vertex exchangeable network for a countable population is dense or empty with probability 1. And this is Aldous Hoover theorem. And so, why is this problematic? Well, it's problematic because we said at the outset the empirical properties I care about are sparsity and power law. And I've already and this shows that if I assume the statistical units of the vertices and I assume exchangeability and consistency, that I'm going to have dense graphs or an empty graph with probability 1. And the reason this is true is because of the fact that the observed vertices comprise a representative symbol, which necessarily violates the notion of a sparse network. Okay, so this leads naturally into this idea of exchangeable interaction networks. Why? Because let's just think about, I'll pick out the Karate Club one again because I already put it up. The Karate Club one is not sampling, but we can think about it, and if you remember the graph, the data you collected was interactions between the individuals in your karate club. It was not, you did not sample the karate members and then look at the edges. And in that sense, what we're really sampling are the interactions themselves. If I think about the Enron email corpus, you'd be sampling the emails and then implicitly seeing employees. If I'm thinking about movies, when I sample from IMDb, I'm sampling movies and I'm getting to see the actors through sampling the movies. So they're incidentally sampled. And so the actors, the employees, the club members are not representative of the overall population, but they're going to be picked in a size-biased way. So let's do the actor collaborations network. I just like these pictures, so it's helpful to me to put them up. So let's think of the sampling mechanism. If I have the IMDb data set, what I'm going to do is I'm going to subsample movies. So let's say I do a simple random sample of the movies, so that I do a similar thing as before. I sample the subset, and I observe a network. Now, this is the actual Enron, or the IMDb data set that's online. I think I have it in one of my GitHubs. And so it's a little weird, but what it really is that each of these is the top actors in a movie with the given labeling. So this movie has actor 4 and actor 5,225. And so the point here is that you have sampled individuals, in this case actors, but you've only done so by sampling the movies. And so the statistical units and the things that you actually want to make these invariance assumptions about are actually the interactions, not the actual actors that you might be interested in. And so formally, what I mean by interaction data is you have a population P, you have EI, which is an indexed set of interactions among individuals in the population. Each EI is a finite subset of P. So for example, for a phone call, EI is a caller and receiver pair. For an email, you have a sender and then a potentially finite vector of receivers. And for movies, you might have just the actors in the movie. And so it's a finite subset of this population P. So just a quick example. It's kind of
on your index for your interactions that you sample?
yes.
Capital I?
Capital I indexes the interaction. So you could have a finite set of interactions or a countable set. So usually we're thinking countable set of interactions. So you have a population here, let's just say of size 10. So the interactions can be countable, but the population that you're studying could be finite. That's a possibility. And so here you have E1 through E6, and these can be represented in the following graph. So there's two labelings going on here that you should distinguish between. One is the labeling of the vertices, and one is the labeling of the interactions themselves. So 1 corresponds to 2, 4, and so on down through here. So the point, I was going to put the math version of this, but it doesn't make it as clear. So the point here is that you have a labeling of both the interactions and the vertices. But it's only with respect to the interaction labeling that you should be assuming the exchangeability assumption. And the labeling of the vertices, you should be quotienting out. So by quotienting out, I mean any labeling of the vertices should give me the same object, so I'm going to quotient out over these potential labelings and get this, what I call the interaction labeled data. So the interaction labeled data only cares about the labeling of the interactions, and I've quotiented out, can't say that, quotiented out, there we go, the labeling of the vertices. So the only thing I'd say is we have this sort of canonical labeling of the vertices, and that's the one on the right, where you can think of individual 1 as the first one you've seen, individual 2 is sort of, you have to make a decision which one's 1 and 2, and then you sort of go in that way. And if you think about that labeling, individual 1 you saw first, but you're also very likely to see him again because he's probably is a size bias pick from the set of vertices, so you're likely to see that individual over and over again. The individual that you label in this way, let's say 1,000, well, they're very unlikely because they're not in that many movies, so you're not going to see them that often. So now I have this object, which is an interaction labeled network, B, right here. And I'm going to make an assumption of what we can call edge exchangeable or interaction exchangeability, which is the labeling of the interactions 1 through 6 in this case. That labeling is arbitrary because I've done a simple random sample. I had to label them to say this is interaction 1, this is interaction 3, but in reality that labeling is arbitrary. And so I'm going to have a random edge labeled network Y and call it edge exchangeable if the permutations apply to those edge labels if you're invariant to that relabeling.
Oh, well.
Yeah.
Dear Wolf.
Uh-oh.
No.
Yeah.
I think I might finally get it after the 10th time. So, if actors chose movies based on the title alphabetical, and you sampled by taking the first 100, then you wouldn't have this. But that's the sort of thing that would break this edge exchangeable.
Mm-hmm.
Okay.
Yeah. So the idea here is that what thing have you sampled, and so therefore we're thinking simple random sampling from a population. So what have you sampled, and what is a representative sample of? And in this case, the interactions are a representative sample of the overall set of interactions, and so that's why we're thinking of this exchangeability in this way.
Quick question. So how do you test if this property is true for a given?
You're killing me. No, I was kidding. It's so it's typically the way we're thinking about it here is that we know the sample. For now, I'm thinking that I know the sampling mechanism. That's why I did the IMDb one where I did it. If you don't know the sampling mechanism, you could potentially try and model the sampling mechanism. So I'm not sure, but in all these cases, we're going to motivate it through the sampling and then assume the exchangeability property otherwise. But yeah, no, I haven't gotten to the testing yet, but I'm trying to move that way too.
I can't imagine being able to do a decent test for
I was going to say
exchangeability.
I can't imagine, but implicitly the graphon models, if you go that route, you're making this assumption, and so you have to make, are you comfortable making either assumption? If you're not, I don't know what you do, but if you have to make one or the other in my head, and so typically there's an obvious choice as to which one makes more sense. You have a?
So yeah, your edge exchangeability is really a statement about invariance to labeling, right? It's not suggesting that whether an edge exists over here is somehow equiprobable to the existence of an edge somewhere else.
Yeah.
Right?
Yeah.
So it's just a labeling invariance statement.
Yeah. It's the fact that all we have done is redecided what we meant by the statistical units and what we meant by arbitrary labeling of those units. And so the arbitrary labeling here is of the interactions, and that's why we're going to assume that they're exchangeable.
Right, but in both cases, you're showing me the exact same.
I'm showing you the exact same. I kept the graph the same, the network the same, but I'm thinking of them as this network you've constructed is coming from seeing these interactions in this order, and not through vertex sampling and then seeing the edges incidentally.
But I think the idea is that you have both edges and non-edges, and they're not exchangeable amongst each other.
When you say non-edges,
Right, so you really got to choose two potential interactions.
Right.
some ones and zeros in your adjacency. maybe.
I see. So the thing I'm going to break up is between so I have not, when I sample the edges, right?
Yep.
I do not have, I'm trying to think of the right phrasing. I do not know when I sample edges, at the end of sampling n edges, how many actors I will see. Let's put it in the movie context. I'm going to label those actors as I see them because I need to be able to distinguish between them. But there's the notion of a fixed number of actors when I sample n edges. That's not the case. And so it's the same thing as if I sampled n vertices, I have n choose 2 edges. Here, if you make the edges all, let's say, binary, then you have a similar condition of the type. The number of vertices you can see. So here I've sampled 6 edges, and I've ignore this guy for now. So I've seen 1, 2, 3, 4, 5, 6 vertices. In the other case, I've sampled 6 vertices, and I so happen to see 1, 2, 3, 4, 5. Well, let's just say this is the one guy. 1, 2, 3, 4, 5 edges. Okay. Yeah.
So in your example with the movies, don't you lose some information if you assume the edge exchangeability, i.e. the number or the larger vectors? Don't you lose it?
So in the generic definition of the exchangeability, we're assuming the interactions are. When we get to the modeling side, I make certain assumptions about how they appear, and that's where I lose it. But in the generic definition, these are just finite subsets, so you can think of them as being seen or not seen every so often. So it's okay, I think. So like in this case, when I sample the movies, I get to see the finite subset. And so the way the exchangeability works is just that the labeling of these movies as such was arbitrary, and so that's fine. But when I get to the modeling, and implicit in the modeling is assumptions about how the actors appear in each of these guys, and that's where things get weird. Okay. I have 30 minutes, perfect. I think I have 30 minutes, right? Yes. So I was going to start with the representation theorem, but I think it sort of bogs down the details of the exact examples I wanted to give. So I'm going to do the representation theorem a little bit later and start with a particular model and use the movie case because it actually makes it a little bit more common. So Harry and I, because I don't know why, we call this the Hollywood model. And the idea here is that we're going to sequentially generate these movies. But at the end of it, you're going to have an edge exchangeable model in the sense that the order in which we generated the movies doesn't matter. So it's a sequentially generated thing. So we have nu from nu k for k greater than or equal to 1, a distribution over positive integers. This is the size of the different movies, the size of the number of the actors in each one. We have a 2-parameter model, 0 less than alpha less than 1, theta greater than minus alpha. And we generate the movies in the following way. And we label actors in order of appearance. This is just so we can distinguish among the actors. For each I, you choose the size of the movie, or in this case, it's the number of roles, because the actors can appear in multiple roles, so that's a minor issue. Given ki equals k, so I've already decided on the number of roles, I choose actors according to the following rule. And if you're familiar with like a Chinese restaurant style process, this is very similar. So the idea here is the probability that the actor is going to be